Hello, everyone. Welcome to the day three of our series of events Navverse. Today, Robotics Club will present Computer Vision Workshop. We'll start in 2 minutes.
Am I audible? Anyone please turn on mic?
Yeah, you're audible.
Yes, yes.
Okay. So I'm Akshat and today I will be conducting the workshop on OpenCV. So have we start? So the topics which will be covering are basics of computer vision, edge detection with some deep dive into Canny edge detector, followed by some about convolution neural network, CNN. So we'll start with very basics like how images are stored, and later we will be following up with various algorithms and a deep dive into Canny edge algorithm. Okay, so what is OpenCV? OpenCV is just a library of programming function mainly aimed at real-time computer vision. So many of you must have thought like, what is computer vision? So we have dealt with it later. So it's just a library containing various functions. So we'll start with basic of computer vision, and in which we will discuss how images are exactly stored in our computers. So you can turn on your like that collab file which we sent. I will send on chat only. Just Is the link viewed by all? Anyone please confirm?
Yeah, you can view it.
Yeah, so open the first link, part 1 Canny.
Can you set the document link again?
Oh, it's in the chat. Please see.
I joined right now, so
Okay, I'm sending it again. I've sent it again. You can see to it.
okay, thanks.
So we'll be starting. What is computer vision? So computers are all about zeros and one, and computer vision is all about teaching zeros and one how to see. So let's skip to a formal definition. Computer vision is a field of having a computer understand and label what is present in an image. Given a two-dimensional image, a computer vision system must recognize the present objects and their characteristics such as shapes, texture, colors, sizes, spatial arrangement, among other things, to provide a description as complete as possible of the image. Like you can see here is an image, how that algorithm is detecting various cars and lanes. So it's the purpose of computer vision. And followed by image processing. Image processing is focused on processing raw images to apply some kind of transformation. Usually the goal is to improve images or prepare them as an input for a specific task. For example, changing color, texture, noise level of image. You might be confused about noise level. We have dealt with it later also. We have dealt very deeply about noise. Computer vision is solving many complex problems such as facial recognition and many other things. So we start with how images are stored. So we'll start with the black and white images. They are stored in grayscale format. Like images are stored in the form of matrix, and those matrices are filled with numbers. Those numbers are called the pixel values. Moreover, the dimension of that matrix also represent a dimension of that image. Like you must have seen a JPG of size 24x16. So it's the size of that matrix which is storing those pixel values. If 24x16 is a dimension of that image, then 24 pixel values along the height and 16 pixel values across the length. You can say see here is an example denoting the pixel values of a 24x16 image. Moreover, the pixel values lies between a range of 0 to 255, where 0 represents the pure black color and 255 represents the pure white. Like you can see, these are the black one. Black are represented by 0. Like it's 11, so it's near to 0. So it represents a dark shade. 255 represent lighter shade. So these blocks which are lighter are represented like with 200 to 250 range of pixel values. So I have a question. What if the pixel value is greater than 255? Will there be an error or something? Or Python won't understand what is happening?
I think we'll start over. Like if 256, then it will count it as 0.
Okay. Anyone else with anything?
It will take 255 only.
Okay.
I think it will take error.
Okay. So
Depends on how the code works.
I think it will change it to a 16-bit number instead of an 8-bit number.
No, actually it doesn't do like that. So I'm telling you what it actually does. It linearly increases that value. For example, if we put a pixel value of 400, so it will find which is the maximum value in that matrix. Here is 400. So it will map it to 256. 400 will be 255, sorry. 400 will be delta as 255 now. You can see here, you can run this snippet also. Like see, 255 represented a lighter shade. So now 400 is representing that light shade. And 257 will represent a range of something between 150 to 200. So it will be a gray one. So do you understand?
All right. So is it kind of relative, like a relative scale is decided? between the max and the min. Hello?
Was there an issue in understanding this thing?
No, I was asking, is it like a relative scale which is decided if it increases after 255?
Yeah, kind of that only.
All right, got it.
Okay. So this is how a black and white image is stored. So following up how colored images are stored. So colored images are stored basically in RGB format. So instead of having one matrix, we have three matrices over here to represent a colored image, namely red, green, and blue. These matrices are called channels. So a colored image is stored in three channels, the red, blue, and green. Okay. So we are open to questions. If you have any questions about image storage, we will be following up with Canny as detector, which would be taken up by RN.
If we take like the maximum value, if we increase to 400, say suppose we have increased to 400. So like the
Okay.
number of shades that I can access from 0 to 250 will be increased, no? If I'm taking 400 as maximum.
So it will just relatively grade those colors, relatively lighter or darker shades.
Okay.
Yeah.
Hello everyone, I am Aryan and now we'll start the coding bit of the workshop. And first we'll start with the first now we'll start with the Canny detector. So if I come back to the image, so all of you, first of all, if you open your Collab notebook, first of all go to this file button and press save a copy in Drive. By saving a copy in your Drive, you'll be able to edit and change the code in this Collab notebook, and you'll be able to run your own coding bits. So everybody just go to the file section and press save a copy in Drive, and then you'll be able to edit this notebook. Till now you don't have edit access, but then you'll get the edit access. And people who have done make a copy can just raise their hand in the chat and I'll get an idea and we'll move forward. Okay, so I think so everybody gets the idea how to make a copy. So now we'll start, first of all, start with edge detection in an image. So the first question that comes in edge detection is, what is an edge for a computer? Any image in a computer is like a 2D image. So how does a computer actually comes to know where is the boundary of a particular object and where does the other object starts? How do you define an edge in a computer vision? So the simplest method for this edge detection we'll be using is a sudden change of colors. Wherever in the image we observe that there is a sudden change of colors, either in the X direction, Y direction, or any angle, we'll try to define that sudden change as an edge. In Opencv, there are many edge detection algorithms which are mentioned here. For this workshop, we'll focus on Canny edge detection. It is one of the most widely used edge detection in Opencv and also gives quite good results. But let's be honest, just simply importing Canny from Opencv and running it over an image is a 3-liner code and there's no fun in it because you don't get to understand how does a Canny algorithm work. Just simply import it and run. So for this workshop, we'll write our own Canny edge detection algorithm. And then in the end, we'll compare our results with the results of the actual Canny algorithm. So we'll be able to see that how to write a Canny algorithm from scratch. So for people who have made the copy in their Drive can come to the first part, and here we are doing all the necessary imports. You can just run this code cell by either pressing this play button here or shift enter. So we can see the code, the code ran. So in all the imports, we are mainly importing NumPy, which will help us to handle all the arrays. As we know, the image is stored as an array in a computer. Matplotlib will help us to plot the images and see the results. And this image is to take the input and the output of the image. Okay. Then we run the next code block, which is getting the data. So we'll have basically two images. We have first is of an IITK image and second is NTU. So after running this code block, you can see it infected IITK.jpg and NTU. So you can come into this folder block here and you will be able to see two images which are there, which is NTU.jpg and IITK. Just run these two code blocks and we'll get our data. And now we can start working on the code. Is everybody following till now?
Yes.
Yeah.
What did this code do, which we ran?
We ran two codes. The upper code was for all the necessary imports. Okay, so in Python, there are many different libraries or a set of codes, and we don't have to do each and everything from literal scratch like I think you guys do in ESE 101. Here we import some of the already ready-made codes, like NumPy actually has some library, some functions which help us to operate arrays very easily. We can multiply or handle arrays. Matplotlib plots help us in many things, but here we are using it for plotting images. And time is obviously time, and schemage is for input and output for the images in this notebook here.
Are these libraries like directly getting loaded into a system?
Yeah, directly. But you have to run the code cell, and it is directly getting loaded into your system.
So like if I have Python downloaded and I try to access it from there only, I will be able to access these libraries.
We are running this
system.
code in Colab notebook, so you don't need to download Python. Colab has Python installed in it.
I know that, but in case if I try to do it, then I'll find these libraries already there on the system.
Actually, no. You have to pip install NumPy or Matplotlib. You can just Google them. How to install NumPy in Python. Yeah, it is basically pip install NumPy.
Okay.
Okay, but I recommend running it on Colab for the time being.
Okay.
Okay, in the second, we just got our data. It's a drive node, it's a Google Drive. We just made ourselves and to get the data. Okay. So the Canny algorithm is basically divided into 5 main sections. The first one is smoothing, and we'll now start with the first part, and that is smoothing. Now in smoothing part, what we do is we blur out the image. Now a simple question arises. Our whole motive of this workshop was to find the edge, and blurring down the entire image defeats that purpose. So why are we blurring? Why are we smoothing out the image, or why are we blurring an image? So the simple answer to this question is because there is a lot of environmental noise in our image. Suppose you're standing against a wall and you want your edge detection on that image. Basically, you are interested in the edges of your body, and if a table or a chair is around you. We don't need the edges of a small flaws in the wall, paint variations or cracks, right? Because there are just environmental noises and we don't actually need them. So by smoothing down the entire image, we actually remove all these unnecessary noises and we actually get a blurred image. However, that blurred image has almost all the noise removed. So smoothing is actually a very important part for Canny edge detector. So now how do we smooth on an image? So if we have an array here, we want something that will move over the entire image, blurring it step by step. Okay, and the thing that will move over the entire image, we'll call it a kernel. So how does a kernel actually work? Suppose this image, we can see in this image here, this big matrix is actually the image here, and this small 3 by 3 matrix is an kernel matrix. Kernel matrix can have any values. Here, for example, we have 0, -1, 0, and all those values. So what really happens is these values in the kernel matrix are multiplied to the values which are adjacent in the image. So this 0 will be multiplied to 105, -1 to 102, 0 to 100, and so on. Whatever values we get, they are all added up and are placed at the center of the kernel matrix, which here is 89. In the next step, as we can see here, this kernel will move one step towards the right. And first the kernel was here, it gave a one value of the pixel. In the next step, it moved towards the right and then gave us a second value. So this kernel actually moves over the entire image and do some processing. What processing we'll come into now. Did everybody understand basically how a kernel moves over the images, and basically we're taking the weighted averages of all the pixels that are underneath that kernel.
I didn't understand how do we select the values in the kernel matrix?
Yeah, values are completely in our hand. We can keep any values that we want. For this specific, even for this specific code, you can keep any values, but however, we'll be using a standard set of values, which we'll call a Gaussian kernel, which the formulas is given here for every value. You can keep any value, by the way. It's completely up to you.
So like mathematically, what exactly is happening? Like I understand what the Gaussian formula is doing. It's
okay. I'll come to the Gaussian formula and come to the mathematics. I just wanted to confirm that we got the idea that how are we multiplying and adding up the values.
Yeah.
So now we'll using this principle to actually smooth the image. So can you smooth the image? Suppose there's a pixel at value of 100 and the other pixel at 250, and we want to smooth out the image. So there can be many ways. One of which is reduce the 250 and increase the 100 proportionally to the distance difference. Suppose 250 is reduced to 200 and 100 is increased to 150. So they got a bit normalized. Or the other method is I can simply keep 250 as 250 and increase the surrounding pixels accordingly. So it will actually blur out the image. What I mean is, if you come down here, we can see here that if this was a test image with just one bright pixel in the center, and if we blur it out, we actually want the final result to look like this. Means that white edge is actually pura फैल गया वो पूरा bright edge एक final result में. So this is how we can actually smudge the image. And for this purpose, there's a standard set which is called Gaussian kernel, whose formula is given by this. So if a 3x3, if you make a 3x3 kernel, we get these values 1/16th of, and these is the value of Gaussian kernel. As you can see, it is just taking averages of all the pixels. Center value is given, the center pixel is given the most value, and as you move away from the center, the weights are decreasing. So 41 in the center and 159 in the center. So as you're moving away from the center, their weights are decreasing. So it gives us a general intuition that we are actually blurring down the image.
By how much does it decrease? How does it decide that?
Yeah, it's how you are asking how much does it decrease?
Yeah,
right?
from moving outwards.
It is not me who has decided. It's a standard Gaussian kernel. That's a predefined formula for it. These are all values defined. We calculated after running this formula.
Okay, so like by changing the values of the kernel, we can also control how much we are blurring the image.
Yeah, exactly. The sigma here is actually a variable, and if we increase the value of sigma, we can increase the blurredness, and conversely is also true.
Okay.
Okay, so we'll now start writing the code. So you can code along with me. So you can come to define Gaussian kernel, and we can start coding. So first of all, we just define a kernel and just fill it with all zeros. So if it's a 3x3 kernel, it will just fill 0 everywhere here. And now our step will be to fill all the values in the kernel iteratively. So first, I will just define this 1/2 pi sigma square. 1/2 pi sigma square. So I'll just define a is equals to 1/2 into n. We have already imported numpy, and pi can be imported as np.pi into sigma square. Okay. So what we got is we got a, that is what this was 1/2 pi sigma square, and now we'll start filling up the values. For that we have to iterate over every value in this kernel. So simply say for I in range 0 comma size for range 0 comma size So with this nested for loops, as you might have done in ESC 101, we'll actually go over the entire matrix. And now we just have to fill the values, that is kernel of I, comma j has to be equal to, this was 1 by 2 pi sigma square. In our code, it is A. So it is A into E power, that is np.exp. .exp I minus k whole square and j minus k whole square. So and j k whole square. And here actually in the formula it is k, and in our function the k is actually size by 2. So we can just replace k by size by 2. This k size by 2. So we got this, and divided by 2 sigma square. Whole divided by sigma into sigma. Yeah. So we got our, so we wrote the formula of kernel exactly which was given in the formula. Let me just check it. By the way, we have also the doc that we have given to you. We will also be posting the solutions here. So for people who don't know Python or are not able to follow me, they can simply copy the code from here and then paste in the code here section in your notebooks. So I think we'll paste the code, we'll paste the solution in the notebook once we are done with this particular function. Okay, so I wrote this code, I'll run it. Okay, so now we have defined a kernel, and the only thing left is to define a simple function that will move that kernel over the entire image. And for that, we'll pretty much be using the conv2d part of the, we'll use the convolved 2d part of the SkyPy, and you can just write here that convolved 2d. So our variable that we are outputting here will be the out. We have just named the variable out. So out is equals to the image here is padded image, our kernel, and it's just a method of writing here, and it has a mode equals true or valid. So you can just so what we are doing is we define the kernel in the buff function, and now we have also defined a code which will move that entire kernel over the image. We run this code, and we can test it by running this. So we can see this was our original image. So we can see that this was our original image and the final smoothed out image, and this is a blurred out image. Just a minute. Also, as you might have seen, I've given edit access to all in the document, but we feel you are sincere enough not to edit the document yourself. So we just request not to edit the document. Just you can just copy the thing, but do not paste or edit it, please. Okay, so this was our original image, and this was a blurred out image. You can even change the sigma value of here. If I change the sigma to 2, or let's say 2.5, and run this code here again, we'll be able to see that the image, the blurred, it has got even more blurred. For the time being, I'll just keep it to 1.4. You can change your values to sigma according to your comfort, and see the result yourself. We have also made this interactive bit, so you can make your own image. So like the image that I made was all zeros and the center pixel was 250. You can change this and we can see the result for this. You can change this image. If I do the last corner as say, let's say 100 and run this code again. So you can see actually my input image got changed and the result also got changed. So you can actually see how will this entire thing work. Has everybody understood?
What can we put the value of sigma? Like, what is the range that can we put? Like, because I'm getting error on 4 and 5.
I just recommend to keep it between 1 and 2 actually.
Okay, is there any specific reason?
Because just the flexibility of the Gaussian kernel actually.
Okay.
You can increase it. I think just double check your, I think the code that you wrote.
Okay.
मैंने एक बार स्क्रीन शेयर बंद किया, मैंने स्क्रीन शेयर बंद किया क्योंकि मैंने Okay, I think there was some connection issue. Yeah. So with this, the first part got finished, and does anybody has any doubt before moving to the next part? Have you guys understood how we are blurring out the image? Please don't direct message me. Recordings will be provided, I think. Okay, so if nobody is replying, I think I explained it well enough. So we'll move to the next part. Okay, so next part is finding the gradients. And what I actually mean by gradient is in what direction are the colors changing?
Hello.
Yeah.
Actually, I'm seeing an error in the last code, the last code that we ran, the blur one.
You can just copy. See, here is a standard solution, and we have posted the solution on this notebook here. You can copy. You can compare your solution with this part.
Okay. Okay.
Yeah. So we are pasting the solutions here for anybody who's not able to follow. Okay. Yeah. So we move to the next part, that was finding the gradients. So now we have blurred down the image, and now we'll start taking differences of every adjacent pixel, because as I mentioned in the beginning, edge is actually a sudden change of color. So how do we get the color is changing? Suppose a pixel was 100 and the next was 250. This was 100, 100, 100, 250. So we can take the difference of every adjacent pixel and see the difference. If the difference is high enough, means there is a sudden change of color. And if you remember correctly, and for different, and that means we'll actually differentiate the image along the x direction and the y direction. So we so the differentiation of the image will be defined as del I by del x and del I by del y. We know by standard formulas that del I by del x will be x plus del x minus I of x divided by del x, and where del x will tend to 0. And similarly, we'll do the same thing for y. Now, anybody in chat can tell me what is the smallest unit of an image? What is the smallest unit of an image?
Pixel.
Pixel.
Exactly. And what is the smallest distance you can move?
One.
In the
Pixel.
One, exactly. So the del x can be converted. Del x can be actually written as 1 pixel here. So we just replace the del x with 1 here. And what we get is del I by del x is I of x plus 1 minus I of x minus 1. What I mean by I of x plus 1 is I is the image and x plus 1 comma y is the address of the pixel, minus I of x minus 1 by 2, and similarly for y. This can also be interpreted as when we are differentiating along the x direction, we are actually taking the difference of a pixel which was present in front of it, that was x plus 1, and the pixel which is present behind it, that was x minus 1. You can see x plus 1 pixel in front and x minus 1 pixel at the back. So if our image was x1, x2, x3, if this was our input image, can we run this kernel here and get exactly the same formula? You know how a kernel works now. So this minus 1, if I run this kernel over this image, this minus 1 will be multiplied to x1, it will become x minus x1, 0 will be multiplied to x2, and 1 will be multiplied with x3. So in the end, we'll get x3 minus x1 by 2, which is exactly this thing, which was x plus 1 minus I of x minus 1. So what did we find out? That a partial differentiation of an image in x or y direction can actually be represented by an image into a specific kernel. When it is for x direction, it is -1, 0, 1, and when it is for y direction, it is just a vertical component of -1, 0, and 1. So the next bit is just to write down these kernels. So you can simply define partial x here. So the partial x here can be written as, so we can just define the kernel dx here. The out is out. So the kernel will be dx, and it will be okay. So np.array, again, we have to make an array, and it has to be 0.5, because -1 by 2 is -0.5, sorry. -0.5, comma 0, and comma 0.5. We also have to ensure that it's a horizontal kernel. So we'll also do reshape. And we'll reshape into a horizontal kernel, which is 1, -1 here. So this kernel here, np.array, this is exactly this kernel here. Next part is just to rotate this kernel over the entire image, and this can be done by the function that we have already defined. So out, that was our out variable, can be defined as conv, that we defined above, image, comma, kernel. So image, comma, kernel, and we have defined a partial x here. We can just run this code directly. And similarly for partial y, we can just copy it here. It's exactly the same thing. This is tiny bit change. Now, for the partial x, the shape was 1, -1. That was the horizontal. In partial y, the shape will be vertical, which will be the opposite of it, which will be -1, 1. So we can just reshape it to -1, 1 and run it. And that is it. We can just test it over the kernel. And here we go. So we can see when we differentiate that, so we can see how drastically the image has changed. This is when we're differentiating the image in the x direction, taking the difference of every adjacent pixel in the x direction, we get this result. And we do the same thing for y direction, we see this result. You can obviously see when we're differentiating along the x, all the vertical edges are getting highlighted. And when we're moving across the y direction, all the horizontal edges are given more attention. This is the main difference between these two images. Here, vertical edges are highlighted, here, horizontal. Have you guys understood how we are differentiating the images in x and y direction?
Can you explain that kernel and partial derivative part again?
Okay, so have you understood that how we are converting this formula here to an image into kernel?
Actually, that's what I wanted to understand.
Okay, so till here, which is just basic maths, we just use the basic formula of differentiation here, and we got that del I by del x is approximately equal to image of, means if we are differentiating an x pixel in an image, suppose ऐसा समझ लो किसी भी image का address xy था और उसके ऊपर हमने अगर differentiation लगाना है in direction of x, so we'll take the difference of the pixel which was present in front of it and subtract it from the pixel which is present behind it, which was x plus 1 minus x minus 1, which was this formula.
Yeah.
And this exactly can be achieved by this multiplying this kernel over an image. See, it is minus 1 here, and this will be multiplied here,
Yes.
and 1 here will be multiplied with x3. So it will
Okay.
essentially so a result of this kernel over this image will be x3 minus x1 in place of x2.
Yeah.
So yeah, so we just wrote the formula, this kernel in terms of in Python, and we got this. And for y, we just change the direction in the y direction.
Okay.
Okay. We have already pasted the solutions in the doc. You can just copy for the kernels. And okay, so now we have got dx and we got dy. So it's just basic trigonometry now.
Excuse me, sir.
Don't call me sir. I'm just
See, in the previous program where the smoothing happened, I got an error of it says index error for the kernel matrix.
okay.
Also, both the images of IITK and NDU, I didn't find them in the files there.
Just run the Google Drive code bit again, and just run this thing again. The second code bit where this is a drive link download. You'll get it.
Okay.
Yeah. So now I'll just wrap this differentiation part. So dy we got dx. So we just have to get the magnitude. Magnitude will be the hypotenuse, which is gx square plus that is and gy square and under root of that thing. And the angle will be tan inverse dy by dx. And we can simply just code it here. Right. So we got the g, which was the g here is the hypotenuse and theta here is the angle. So we can just write that dx here was we have already defined the gx as partial x. We send that image here. We defined a dx. We defined a dy, which was again partial y image. And then we just define the g, that was the hypotenuse, as np dot square root dx square plus dy square. Similarly, the angle theta has to be equals to tan inverse, which can be written as np dot arctan. Not arctan. We have to do it in degrees, so we do arctan 2, not arctan. Dy comma dx, that is dy comma dx. We have to convert this angle into degrees, so we just multiply it with 180 degrees and divide it by np dot y. Modulus 360. So we got a thetas here. So if I just run part, yeah. So we defined a gradient, and if we run the entire partial on the image, just keep in mind before that our result was this, and by just running the this was our result, and now by running the partial differentiation over the image, we got this result. So you can already see we have just done 2 steps now, and we have already got majority of all the edges in the image. Okay, so this was the end of part 2. Do you guys have any doubt till now?
Could you explain how partial derivatives helped in finding the edges?
Yeah, so edges I already defined was the sudden change of color, right?
All right. By that basis, yes. Okay, got it.
Okay. So we are pasting the solutions in the doc file. If you guys are not able to follow, you can always come here and run your notebooks with the help of this code here. Okay, so now we'll move to the third part, and third part will be explained by Arushi. Thank you.
Okay, so now we will come to the next step, which is the non-maximum suppression step. Now, the purpose of this step is to convert the blurred edges into sharp edges. Now, as you will be able to see, the edges out here are quite thick. Now, to convert them into sharp and crisp edges, we will do the step of non-maximum suppression. In this step, we round the gradient direction to the nearest 45 degrees as an approximation. Then we compare the edge strength of the current pixel with the edge strength of the pixel in the positive and negative directions. For example, if your theta is 0 degrees or 180 degrees, you will check in the directions east and west to the current pixel. And if the theta is 90 degrees, you will check the pixels north and south of the current pixel. Now, if the edge strength of the current pixel is the largest, then you preserve it, or else you will discard. So now we will store the dimensions of the image, the height and width in the variables h and w respectively. Then we will define a variable called out, which will store another pixel matrix full of zeros. Now, we will also do theta modulo 360 to ensure that theta remains in the range 0 to 360 degrees. Now we will start the code. Also make sure that the indentation is correct, because in Python, if your indentation is wrong, the code will give an error. So in this, here we see that if theta is 0 or 180 degrees, then you will check the current, just a minute. Then you will check in the directions east and west to that current pixel. And now if the intensity of the current pixel is more than the intensity of the pixels which are on the right or left to it, then you will keep that value, the value of the pixel, otherwise you will discard it. Now we will do the same for theta is equals to 45 and 225, for theta is equals to 90 and 270, and theta is equals to 135 and 315. So I will just copy paste this code and make the changes accordingly. This is for theta is equals to 45 or 225 degrees. So we will check the pixels in the diagonal direction. If anyone has any doubt, they can ask.
Could you explain again what exactly we are trying to do in this portion of code?
In which portion of the code? Like in the entire non-maximum suppression.
Yeah.
Okay, so basically what you do is you take a pixel and you go and suppose that is what we call the current pixel. Then you will check the values of the pixels right and left to it if the theta is 0 or 180 degrees. Now, if the value, the intensity of the current pixel is brightest between the three pixels, which are like, it is brightest among the its own right and left pixels, then you will keep that value. And if it is not that value, you discard that value. And by doing this, you will change the blurred edges, which you saw in the previous section, to sharp edges, which you will see now. Did you get it?
Okay, so like we will first check in left and right, then up and down, and then diagonally.
Yeah, and then you will check north and south, east and west, and diagonally.
So
Did
what
you
if
get it?
what if like in one direction it is the brightest pixel, but in another direction it is not the brightest pixel? Then we will keep it or not?
I didn't get your question.
Like suppose if we take a pixel and in left and if we take its left and right pixels, then among those three pixel it is the brightest. But if we
Yeah.
take top and bottom, then it is not. So
These are two separate steps. So first you check right and left to it. And if it is the brightest, you keep it. Then in another step, you check top and bottom. And if it is brightest, you keep it. Otherwise, you discard it. Did you get it?
okay, I get it.
These are two separate steps.
I also had a doubt. We defined theta to be the like tan inverse of dy by dx, which I get, but is there a like a visual representation of what angle is theta? Like I'm not able to visualize what exactly is theta equal to.
Just a minute, I will tell you. I will just show it to you in the interactive section which comes after this, okay?
Okay.
Yeah. So now theta, we will check for theta is equals to 90 degrees. And now we check for theta is equals to 135 or 315 degrees. Now, if the theta does not satisfy any of these conditions, we will write an else statement, which will say that it's the wrong theta value. And I'm sorry, it's supposed to be LF out here and not if. So this is the code for the entire non-maximum suppression part. And we have also copy pasted this section of the code in the document. And if you are getting an error, you can directly copy paste it from that document. Now we run this part, which will plot whatever we have done in this section by checking all the theta values. So now this is what we get after the non-maximum suppression step. Now you can see this edge is quite sharp and thin compared to what was seen in this part of this portion of the code, where this thick is quite blurred. Is there any question? Okay, so now we come to the interactive mode. Here we have taken a 5x5 pixel image, and you will be able to see that the application of the above part, you will see that if the value of the current pixel, the intensity of the current pixel is the brightest, then you will keep it, otherwise you discard it. Okay, and someone earlier asked about the visual representation of theta. Here you can see that if your current pixel is this and theta is equals to 0 or 180 degrees, then for theta is equals to 0, we will get this pixel, and for theta is equals to 180 degrees, we will get this pixel. So we check right and left to it. Okay, and if theta is equals to 90 degrees, we get this pixel, and theta is equals to 270 degrees, we get this pixel. Did you get it now?
Yes.
So this was the interactive. Now the next part is called the double thresholding. Now in this, the Canny edge detection algorithm uses double thresholding. Okay, so edge pixels, which are you basically define two thresholds, a higher threshold and a lower threshold. Now the edge pixels which are stronger than the higher threshold are marked as strong. Edge pixels which are weaker than the lower threshold are marked as weak, are suppressed, sorry. And the edge pixels which are between the two thresholds, which is lower than the higher threshold but higher than the lower threshold, you mark those pixels as weak edges. Okay, so now here we start the code. We will define two variables, strong edges and weak edges. Strong edges will store if the value of the current pixel is stronger than the higher threshold, and weak edges will store if the value of the current pixel is between the two thresholds, which is between the higher threshold and the lower threshold.
How do we decide the higher and lower threshold values?
You will have to decide it by running it again and again. You will have to see that which values give you correct results. Like it will be a hit and trial. Okay.
Okay.
So as you can see, if the intensity is higher than the higher threshold, you store the value of true in the variable strong edges. And if the intensity is more than the lower threshold, but lesser than the higher threshold, then you store the value of true in weak edges. And we run this code. Now, by various hit and trial methods, we decided that the lower threshold for this code should be 0.02 and the higher threshold is 0.03. And Canny basically has recommended a ratio of a upper to lower ratio between 2:1 and 3:1. Okay, someone asked about the decision of lower and higher threshold. Is it fine now?
Yeah.
So here also we decide taking into consideration the ratio which is supervised by the Canny, we take lower threshold as 0.02 and higher threshold as 0.03. And then we plot the output. So now in this output, you can see that for the image on the right, it has both strong and weak edges, and the image on the left has only strong edges. So as you can see from this part of the code, it will have the variable of strong edges, where we just output the strong edges, which means that we output the pixels which had the intensity which was higher than the higher threshold. Then here we also initialized a variable called edges, which stored the full intensity of strong edges and half the intensity of weak edges. And then for the variable edges, we get the plot on the right, which has both strong edges and weak edges. Is it fine? Is there any doubt? Anyone?
When we are taking half of the weak edges, is that also through hit and trial, or like is it fixed half only?
Can you please repeat the question?
I was asking that when we are taking when we are taking half of weak and the strong completely, so are we just doing hit and trial to find which like combination gives us the better picture?
Yes, we are like right now we showed it with 0.5. You can also try any other value. There's no
Okay.
specific thing that you have to take 0.5.
Okay. Why is it necessary to classify the edges as strong and weak edges?
Because sometimes there are many edges which are not necessary. Okay, so you need to remove those edges, and some edges are not very strong and not very weak, but they are necessary. So to use to make the picture come out nicely, you do this. Did you get it?
Oh, okay.
Any other doubt? Okay, so now I will be handing it over to Dishay for the next parts.
Hello, am I audible?
Yes.
Okay, yeah. So I am Dishay Mehta, Secretary at Robotics Club IIT Kanpur. Now I'll be taking over for the fifth part of the Canny algorithm, which is called as edge tracking. So basically, we have two edges, strong edge and a weak edge, as my colleague Arushi had already mentioned. So there is one common thing which we have to figure it out. Like there is an error in this problem, so we have to figure it out. So I'll tell you what the error is in our Opencv, this Canny algo. So basically, strong edges are interpreted as certain edges and can be immediately included in the final edge image. But now we have to consider its neighbors iteratively, and we'll declare it as an edge pixel. Now, if it is connected to an edge pixel directly, and there are two cases, like either it is connected to an edge pixel, a strong edge pixel, or it has pixel values between low and high. If the values are below low, then it will be discarded. It will be treated as noise. So the logic is, of course, that noise and other small variations, they are unlikely to result in a strong edge. Thus, the strong edges will be the true edges of the original image. As you can see here, this is the image with only strong edge, and it is uh, having very less noise. But strong edge plus weak edge has some noise, and it is making it blur. Yeah, so basically the weak edges, why do the weak edges arise? Like they can either be true edge, which are masked, or they can either be noise. And the weak edge can be distributed independently of the edges of the entire image. So basically weak edges due to true edges are much more likely to be connected directly to the strong edge. So in short, the concept is that a weak edge near a strong edge is actually a strong edge, and it is not a noise or something. So for tracking the weak edge, which is actually a strong edge, we'll define some functions. So first we have defined a function called getNeighbors, and we have just initialized an empty list called neighbors, and then we are running two for loops in the range of three elements in y and x, and then we are setting a condition that if I equals to y, like, and if j equals to x, like in the grid the index is matched, then we'll just append the list. We'll append the elements to the list, and after that we'll get the whole neighbors, the list of neighbors, and then we'll just return the neighbors. Then the second function, which is the main function, called as linked edges. So what this function will do is that we have two lists, one having strong edges and other having weak edges. Now we'll make another list having, it basically links up the strong and the weak edges, which are actually strong in the final list. So that the final linked edge list will have the actual strong edges of the image. So firstly, we have defined h comma w equals to strong edges dot shape. So strong edges basically having a height h and width w, and then we have defined a numpy stack of indices, which which takes basically strong edges, the value of strong edges, and we have initialized the edges list to 0. Like we have written numpy np dot zeros with input parameters h comma w. So the shape is the same as h comma w, our shape of the list, and the default type is defined as boolean, so it will be true and false. Okay. Now we have to make new instances of the arguments to leave the original references intact. Like here we have used already strong edges and weak edges, so we'll just make a copy of those to the new list variables, like called weak underscore edges and edges. So now we'll start basically coding. So now this will help us link, like what is the code behind linking up of the lists. So basically we'll have to define a queue. I'll tell you why. So for that we'll first do for, I have to write a for loop. 1 minute. My bad. Yeah. In indices, as I told you, indices are the stacks of strong edges, and we'll define a queue equals to get underscore neighbors, get underscore neighbor with parameters m comma n comma h
comma W. Okay. Then visited equals to, I'll explain the code in short. I'll first write it down. UEUP. Q dot pop 0. So basically what I've written till here is putting the values of m and n there and making a queue of the neighbor function. And we'll visit the queue. So that is why we are doing while queue, and this will end when the queue has 0 elements. Okay, so we are initializing y and x as the first element of the queue. So we are doing q dot pop 0.
Could you repeat? I think the net went off.
Okay, yeah, sure, I'll repeat. So basically, I'll tell from the start that we are using a for loop to basically iterate through the x comma y of the indices list. Okay, and then we are basically declaring a queue variable, which is a queue data structure. Sorry, and we are writing q equals to get neighbors m comma n comma h comma w. Basically, what it does is the output of this function, it will return the neighbors. So that will be stored in the queue itself, and then we are accessing the elements of queue using a while loop, and we are basically popping the elements of the queue one after the other. So eventually the queue will end, and so will our while loop. So then we are firstly initializing y and x as the first element of the queue. So we are using y comma x equals to q dot pop 0. Then if y comma x is not in the visited, not in visited. So we have here defined an empty list visited. So visited, we'll append the neighbors which we have already visited in this list. Okay. Visited dot append. We'll append y comma x. Okay. Then we'll check if there are weak edges available. Weak edges y comma x. It will, as I have already defined weak edges, and the default type is basically Boolean, so it will just check if it's true or false. If a weak edge is present, then we'll have to check. We'll have to check that if it is present, then we'll have to assign it to our strong edge. So we'll write edges y comma x equal to true. Then q dot extend get underscore neighbor. Y comma x comma h comma w. Okay, so this what I've written within the if statement is that if we have come across a weak edge, if that is present, then that weak edge is actually a strong edge and not a weak edge. And we are extending the queue with the new neighbors now, because this we have done for in the start, but we'll have to extend we'll have to basically update the queue also. I'll just run this part. Okay. So do you have any part in the code? Because the code might be tough to understand, but a visual interpretation might help you in better understanding. So if you have any doubt in the code, tell me.
Then I'll move
I
on to
didn't understand how you were deciding which weak edges were actually strong edges.
Okay. So the weak edges, which are actually near the strong edge, are not weak edges, because weak edges can only be weak edges if they are purely noise. But if a strong edge is near that particular weak edge, then it will have some influence on it, and it will be within the strong edge region. So it will have no component of noise, and it will be a strong edge. So that is what we are using. That
Okay.
the weak edges due to true edges are more likely to be connected directly to strong edges.
How exactly do you check if it is near or not?
So that is why we have defined the neighbor function. The neighbor function basically has all the neighbors arranged. Basically, wait, let me first show you the interactive mode, because that will be intuitive. One. Okay, I didn't define the function. So this is, yeah. So now you will be able to understand the visual interpretation of what I'm trying to explain. So let us first define a 4x4 kernel of strong, which is a test strong. So these are the strong edges. And since I have defined it like as zeros and ones, zeros mean that a strong edge is not present in that particular part, and one means that a strong edge is present. Same for the weak edge. So this will actually be equivalent to this interpretation, wherein the one was here. The one here actually means the strong edge. So it is represented as white. So there are 3 strong edges present initially, and 3 weak edges also present in the particular example which I'm explaining. So now what I'm trying to say is that we'll first take a look at the strong edges, the image of the strong edge. So do you find any the image of the weak edge? Do you find any strong edge near the weak edge? Near means within, like surrounding it.
The last and the weak is the bottom one. It's like 1.5 to 2.5. It's surrounded by 2 strong edges.
Very good, very good. So this it is surrounded by two strong edges. Then it would mean that it is definitely a strong edge and it is not a weak edge. So we'll have to correct that. So we are basically linking that weak edge into the strong edges list. So that is what this function link edges will do. It is basically it is making queues and then removing the edge from weak edges list and appending it to the strong edges list and making it name as linked edges. And in fact, even this weak edge, it is surrounded by one strong edge. So it should be at least one. And this also satisfies the condition. So this edge is also a strong edge and not a weak edge. And similarly for the third weak edge here. This is also having in proximity this strong edge. Therefore, this weak edge is also a strong edge. Now let me just play along and give you one more example. And do 0, yeah, and do 0, and this has 1. Okay, cool. I'll run it again. Okay, so now in this new example, we have 2 strong edges which are along the diagonals, and we have 3 weak edges. So now we'll, as I said, we'll first monitor the weak edges, and taking this weak edge first, are there any strong edges nearby? Nearby means that just a pixel away, like either top, bottom, left, right, diagonals.
No.
No, very good. So this weak edge is actually a weak edge and not a strong edge. So we'll not link that. Then we'll move on to the second weak edge. Is this weak edge surrounded by any strong edges?
It is. It has 1 at the left side.
Yeah, very good, very good. So that weak edge will be what? Which edge?
Linked edge.
Yeah, it will be a strong edge actually, and so we'll link it in this. Now moving on to the third weak edge. It is also not surrounded like in near proximity to any strong edge. Therefore, it will be considered as a weak edge only, and we'll not link it. So our final linked edges kernel will be this as shown here. So now we are basically in this segment, we are just trying to figure out, we are basically trying to improve the performance of our image detection. Like because the weak edges may cause trouble, and we have to remove the noise. Basically, noise is redundant, so we'll have to remove that. And in removing the noise, we'll have to just check whether the weak edge was considered as noise or a strong edge. And if we by mistake considered a weak edge as a noise, but it was a strong edge, then it would cause a mishap. So we are with this part, we have just checked what was the final, if anything went wrong, and we are done with that. So if you have any doubts, do let me know. No doubts? Okay, I think I'll move on with this segment. Okay. So after linking the edges using the link functions, like, and finally saving the image with the name edges underscore result, the final image is shown here. Now you can see there is much difference between this image, which has final noise, very reduced noise, and the image which is shown above here. As you can see, there is hardly any noise in this image. It is as if it's hand drawn, like without any noise. Any dot. Yeah, so we'll now we'll combine all the functions which we have defined above, and all the 5 parts we'll write it in a single function, Canny, and let me run it. And yeah, for the reference image, we have taken the photo of OAT, and we'll run that. And here, as a reference image, as a reference, we have used Canny, which is a function in the Opencv library, this to just check if how much deviation is our algorithm showing from the actual Canny algorithm in the Opencv. And here are this is our result on the left, and this is the reference which we have obtained from using the Canny function. And as you can see, there is hardly any difference. Like there might be 1% of difference only. So this is a great achievement. Like we have done everything from scratch and not used just 2 lines of code, but we have understood the concepts also. What actually happens and how do you have to move from one part to other. Any doubts? Hello? Do you have any doubt? If no, then we'll move on to the next part.
No.
Okay.
One doubt I had, like when the border is at an angle, it is basically reflecting that as a combination of horizontal lines. So like, can that not be improved so that it is like just a uniform line?
But there are certain more complicated models, like it will just complicate your model, and there are some of them available. And like Canny is just a basic edge detecting model. We have many more such models for that. Like it has better results than Canny, and we can implement it from scratch, and we'll have to include basically more functions. So that is possible. That's a actually very good point which you pointed out.
Okay, understood.
Anything else? We'll just take a 2-minute break before we move on to the next part. Which is convolution neural network. Okay. Yeah, actually, before moving to that, I'll just tell that what are the applications of edge detector, that why are we using it. So as you have seen that in fingerprint scanning, every person has a unique fingerprint, and basically we have to identify the edges of our fingerprint. So we have a great application of edge detector there, and even in self-driving cars and robotics vision and license plate detection, like we have to use the concepts of image processing and edge detection to just identify that what is the number plate, etc., all those. So these are the applications. And yeah, now we'll take a 2-minute break.
Hey guys, so now we'll be moving on to CNN or convolutional neural networks. So what basically is CNN? It's a deep learning neural network which is sketched for processing structured arrays of data. And it's composed of two basic parts, which are feature extraction and classification. So what is feature extraction? It involves several convolutional layers, which is followed by max pooling and an activation function, which are some terms that just take it at face value right now. You don't need to like look too much into it and just take it as it is. So what feature extraction does is it takes raw data and it transforms it or like converts it into a form which can be processed by the computer. And classification is basically taking an input image or a data which can be processed and outputting a class or the probabilities of various classes that the input image might be in. So it works by picking up design from images like circles, lines, or like various shapes, and even more complicated shapes such as the shape of an eye, like the sort of the outline of an eye, or even the outline of a shape of a face, or so on. So a particular kind of layer called the convolutional layer forms the basis of CNN. And a CNN is basically consists of many convolutional layers which are assembled on top of one another. And the order in which these layers are assembled also helps CNN in recognizing the attributes or like the features in the image. So what is convolution? It's a mathematical operation which is used to merge two sets of information. And here the convolution is applied on the input data, which is the image on the left side, and it is applied using a convolutional filter or a kernel, which is given on the right, to produce what is called a feature map. So I'll be explaining feature map briefly in the next section, but just to give you a brief idea of what a convolution layer does, it is capable of recognizing shapes, and the more number of convolutional layers that you have, the more viable it is to recognize more sophisticated shapes. Such as it would take you about 3 to 4 layers to say recognize or identify handwritten digits, and about 25 to identify a human face, just an approximation, of course. So here we move on to what convolution actually does. It's performed by placing the filter over the input and performing element-wise matrix multiplication and placing it in the corresponding position in the feature map. Now that might sound complicated, but it's pretty simple. So what you basically do is you take the convolution filter or kernel, which is a matrix of the order 3 cross 3, and put it or like overlap it with the input, which is a matrix of the order 5 cross 5. So here we assume it to be 2-dimensional. It's actually not, as you guys already know by now, but we're assuming it to be 2D right now for this point. So suppose you put it overlap it with the leftmost top part here. So you just multiply the elements. So like you have 1 into 1 for the leftmost, and then you have 1 into 0, and then you have 1 into 1, and so on. So what you do is you just multiply them, and then you add the values up. So like 1 into 1 is 1, 1 into 0 is 0. So like this, you have 1, 2, 3, 4, 4 ones, and the rest 5 are zeros. So you just add them up to get a 4, which is shown here. Then you shift the convolutional filter or the kernel, which is also called that, just by say a position to get another element of the feature map. So the feature map is like an output of the convolutional layer when you input the image and the filter as well. So you have 1 into 1 here for this, 1 into 0. And similarly, if you just add the values up, you'll get 3 ones and the rest 6 are zeros. So you get the output of 3. So like this, correspondingly, you can find all the elements of the feature map. So as in this example, we took these inputs and the filter and the feature maps to be 2-dimensional, but as you already know, the input image is actually 3-dimensional. So since you're kind of overlapping the input image with the convolutional filter, it makes sense for the convolutional filter to be 3-dimensional as well. And the depth of this filter should match the depth of the input. Now, the convolutional filter operation, which is performed for each filter, is performed independently, and the resulting feature maps are disjoint. So like for a CNN, you won't just have one filter, you'll have multiple ones for even just a single layer. So the outputs or the feature maps that each filter produces are disjoint. So like for this filter here, which is red, say, this red slice on the right will be produced, this feature map, the red one. And for the green filter, the green feature map, which is on the right, will be produced. And these are disjoint, so they don't overlap. Now next, moving on, we perform multiple convolutions on an input, and each using a different filter and resulting in a distinct and disjoint feature maps. So convolutional filters are 3-dimensional, as I've already discussed. So we then stack all these feature maps together, and that becomes the final output of the convolution layer. So just for an example, let's take this picture here, which has an input image of 32 cross 32 cross 3. And yeah, just a minute. Yeah. And a convolutional filter of say the order 5 cross 5 cross 3. So how you get the feature map is basically by kind of sliding the convolution filter all over the input image. And as you can see, the depth of this filter and the depth of the input image match. So that's 3, and that's this is also 3. And then you slide it, and for each position you get a particular result, which is, suppose for this random position you get this point, which is like 1 cross 1 cross 1, this point in this matrix. And then you aggregate all these results by sliding the filter over all the points in the input image, and you get the resulting feature map, which is shown as the red slice on the right. So this is just for one filter, but like I mentioned, we have multiple filters even in a convolution layer. And suppose we have 10 filters for this layer. So you will get 10 distinct and disjoint feature maps. And if you assemble them together, like stack them along the depth dimension, you will get the final output of the convolutional layer, which here is this big blue box of 32 cross 32 cross 10. So as for CNN, we plan to keep it till this for all of you. You have been given these links, and you might notice that there are quite a few codes which are following up. We don't plan to delve into these because we feel like we've already covered a lot, and it might get really kind of overwhelming. So we'll keep it at this. You have the resources available to you if you can choose to go over them. If you have any doubts, feel free to contact us. This is all for now. Thank you for attending this session. I hope you enjoyed it. I hope you learned a lot. And I know it was kind of like, overwhelming, I guess, a lot of news shit and all. So thank you for attending. Have a great day. Thanks. Bye-bye. Yeah, someone raised